We have one more problem to look at in the world of hypothesis testing, and that's something called a paired t-test. This is our last problem, problem number 11. And in this problem, we have 22 mid-level managers, and we measure some sort of metric associated with their work, successfully completed projects. And then in the second half of the year, that was in the first half of the year, the second half of the year, we offer an incentive in the form of comp time for each project completed. And we were wondering whether or not the application of that treatment, the comp time, makes a difference in the number of projects completed. So let's take a look at our data. We look at our data. Here are the individual observations. Each observation, by the way, is an individual. This is individual number 1, number 2, number 3. And this is the first half of the year. This is the number of projects completed. In the second half of the year, this is the first half of the year. This is not receiving the incentive, and this is receiving the incentive. So you can see that person number 1 went from 90 to 95 after the incentive. Person number 2 went from 85 to 89, etc. Not everybody has to go up, but it looks like many of them did from this. Here's one that went down, and another one that went down, and actually another. So let's see if that incentive, in fact, makes a difference. How are we going to do that? Well, we're going to use something called a paired t-test. And to do that, we go back to our data analysis tool. And one of the tests that's available for us down at the bottom is something called the paired t-test. This test is associated with looking at situations where you have, often the case is that a single observation receives two treatments, not receiving incentive and then receiving incentive. This is often called a before and after test. So we have to look very carefully for these kinds of tests because they take different sort of analytical tools to make the determination. Understanding that this is the same the individual, the same observation, makes a big difference in the analytics. So I go to OK, and then it says, all right, what's variable range 1? I'm going to grab this. It's variable range 1. And then I'm going to grab variable range 2, which is the after condition here. And then I'm going to say there are labels there. The hypothesized difference, we hypothesize is 0. If you put nothing in there, it'll assume 0. And let's see what the results is of the test. Here's the results, and the results suggest the following. Here were the two means. They look fairly similar, although one is slightly larger than the other. The after effect of having had the comp time is a little higher, so maybe it did make a difference. And any of our null hypothesis that we're testing, we always look for a p-value in this type of hypothesis testing. And here's our p-value for a one-tailed test. Here's our p-value for a two-tailed test. So in this particular case, what was our alpha in this particular problem? Our alpha in this particular problem is 0.10. So it looks like we're close. We get 0.10 and a fraction. So this p is actually a little bit larger than our alpha, so we cannot reject a null hypothesis as a result of that. I did the same test here with Minitab, and I get very similar results for this is a two-tailed test. This is a two-tailed test that we see here. So in this particular case, we state the null hypothesis is the mean no incentive, and incentive is equal to 0. In other words, the difference between this mean and this mean is equal to 0. There's no difference, and the alternative is is that there's maybe a difference, but we don't know which direction. So I cannot reject the null hypothesis as a result, because both my values here, p-values, in particular the two-tailed test, is larger than p of 0.1. That's the end of problem 11 and all the problems in module 3.